Hello, everybody. So today, this is not exactly how to do something for calculus question. I was challenged by someone to explain elliptical curve cryptography as a YouTube video. So I've been doing some reading. It has a decent bit of amount of math. That's what this Desmos graph on the side is for. I will link this in the description so you guys can use it. Anyway, let's get started. So, first of all, this is cryptography. So you got one message, you encrypt it into something else. So like dog could go to it could go to some like EFV, thanks to some cipher that's being used. And then you take EFV, which is your thing that your ciphertext. You add your key or whatever it is you use to unlock it, and you can get dog. Or let's say this is like highly secret information. It's like your grades. You don't want anyone else to see these. And then they're just written down as a bunch of text and numbers. And oh my god, it's everywhere. But then you can add this, send it through the key, and now you're able to see what your grades are. And no one else can. So, elliptical curve cryptography is one really good way of how to encrypt how to encrypt really important data into ciphertext and then unlock it later. In fact, it's so good that even the US government has decided to start using it. I mean, they've been using ciphers and all, but apparently this thing is so good, you don't need as many bits or amount of data to do the cipher than you need for other kinds, like more common RSA encryption. So let's start. First thing is, what is an elliptical curve? You probably saw that crazy thing on the side earlier. So an elliptical curve is just a relation with the equation y squared equals x cubed plus some number times x plus another number plus b. And usually I see that this number is negative, so it can like curve out like this. Now the very unique thing about this graph is at most it can only intersect if you take one point, draw a line through it, like we saw over here. Oh my god, this is crazy. Let's remove one. So if we just look over here, at most this line only intersects with 3 points. The minimum is 2, maximum is 3. So yeah, we can just look at it, and usually it will only intersect in 2 spots when it's a tangent line. If you're doing calculus, you know what tangent lines are, how you find them. Anyway, so we have our elliptical function, and we use this for encrypting. Let's leave. Okay, so here is my masterpiece of how I'm going to explain how to encrypt this. So, you got 2 things for your public key. You got your starting point on this curve. I'm guessing the curve is generalized for this. You got your starting point on the curve. You got your boundaries so it doesn't soar off into infinity. I'll explain why you need that boundary. Anyway, this is all you need to start with your curve. Let's close off this one so we can just focus on these 2 top points. So first, we need to have a tangent. We need to find the tangent line of this. Let's pick this as our point for today. And we're just going to do how you do in calculus. You just make a point very close to the original. So we're going to start off with this point today. But how we're going to do it? Because this graph is symmetrical along the x-axis, meaning you can flip the y values and the x value will stay the same. So now what we can do is we are 3.4662. I can just, for purposes of explaining, I'm just going to estimate. But now we got a second line that just popped up. Now the green thing doesn't matter for now. But notice that this line now intersects in a different spot. And then afterwards you go over here, you flip the y value again, you draw a third line, and this one does intersect. You notice it's very awkwardly placed. We insert that. We keep on going. Now it intersects over here. And now you notice that it seems to be a very random process of just going back and forth trying to figure out what points. And this one. See, now this one is all the way up close. And this is where our boundary line kicks in. So notice how there's only 2 points. And now this bottom one is just spiraling off into infinity. But at some point, it hits our maximum boundary line around almost -400. At that point, the line is supposed to loop back and hit our function somewhere else. Let's just assume it's going to hit here. So if it hits over here, that means our function is going to, we're going to redraw the function over here. And now we can continue as normal. So only getting hit at 2 points is not going to stop us for this. We can just keep on going. And after you do this n number of times, you are left with an ending point. That ending point is very useful, but what's even more useful is the private key, which is how many times did it take you to get from point A to point Z. Just given the ending point and the starting point, extremely hard to find. It's called a trapdoor function, meaning easy to get in, hard to get out. RSA has that same principle where you have to find the factors of a number that only has 2 very large prime numbers as its factors. And that's the basis of that entire decryption and encryption. So the fun part of the elliptical cryptography, it's all based on a single shape, this elliptical curve. That's what I liked about it. Is there anything else I can say about this? So our public key, function, starting point, maximum boundary. Remember, you find the starting point by using that tangent line, or in this case our tangent line approximation, to start it off. Computers can find the tangent line very easily. It's all with derivatives and stuff. You take that point, flip it upside down, flip its y value upside down, get a new point, and then start graphing. After n number of cycles, you're going to be left with one ending point, and your private key is going to be that how many steps did it take. Hopefully I explained the basics of elliptical curve cryptography. I'm going to post this graph down in the description so you guys can play with it. You guys can see how this is supposed to work. See you soon. Bye.